Class. Coming to our next topic, that is isomerism in coordination complexes. Class, you have been studying isomerism in organic compounds, but there is isomerism in coordination complexes also. As in organic chemistry, there were two types of isomerism, structural and stereo. Similarly, coordination also shows two types of isomerism, structural isomerism and stereoisomerism. Structural isomerism has been divided into four subtypes: ionization isomerism, hydrate isomerism, linkage isomerism, coordination isomerism. Similarly, stereoisomerism has been divided into three types: geometrical isomerism, FAC, and MER, FAC and MER isomerism, and the last one is your optical isomerism. So class, this is isomerism at a glance. I repeat again, in coordination complexes, there are two types of isomerism, structure and stereo. Structure has four subtypes: ionization, hydrate, linkage, coordination. And stereo has three subtypes: geometrical, FAC and MER, and optical isomerism. So class, we are going to take first the structural isomerism definition, then we'll take ionization isomerism. So what is structural isomerism? Class, for coordination complexes, I'll write CC. Coordination complexes having same molecular formula but different structural formula. Different structural formula are said to be structural isomers, and in that we are going to study ionization isomerism. Class, definition of ionization isomerism: coordination complexes having same molecular formula but give different ions in their aqueous solution. Very important, class. Different ions in their aqueous solution. Class, for example, CO5 ammonia Br.SO4. It can be represented in two forms: CO ammonia 5 Br sulfate outside, CO ammonia 5 sulfate inside, and Br outside. So class, let us first see whether they are having same molecular formula or not. 1 CO, 5 ammonia, 1 Br, 1 sulfate. Similarly, 1 CO, 5 ammonia, 1 Br, and 1 sulfate. So both are having same molecular formula, but class, you know very well, when we ionize, we get sulfate ion in their aqueous solution. In this case, we get bromide ion in their aqueous solution. Class, so if I dissolve in barium chloride, I get barium sulfate, white precipitate. But if I put silver nitrate solution here, no precipitate. Why? Because Br is not outside. But in this case, class, if I take barium chloride and dissolve this complex on it, no PPT, because sulfate is not outside. But since Br is outside, if you treat it with silver nitrate, this is going to give you AgBr precipitate. So both are having same molecular formula, but they give different ions in their aqueous solution. Therefore, they are called ionization isomerism. Class, very, very important, and quite often it is being asked in your even board as well as in competitions. Now class, we'll take up our second, that is your hydrate isomerism. Now class, moving to hydrate isomerism, the definition says coordination complexes having same molecular formula but give different water molecules when treated with Kong sulfuric acid. So they have the same molecular formula, but when treated with Kong sulfuric acid, they give you different moles of water. Just see here. Let us first find out whether they have the same molecular formula. 1 CO, 5 ammonia, 1 H2O, 1 H2O, 3 Br, and you see 3 Br. So they have the same molecular formula. But in this case, since water is here as water of crystallization, So when you treat with Kong sulfuric acid, 1 mole of water will be absorbed. But class, in the second case, water is present inside coordination sphere, and you know very well that coordination sphere is highly intact. It will never dissociate, therefore water will never come out, and hence when this molecule is treated with Kong sulfuric acid, no moles of water are absorbed. So class, in the first case, since water molecule was outside square bracket, so 1 mole of water was absorbed when treated with Kong sulfuric acid. But in the second case, since water was inside coordination sphere, so no water was absorbed. Then class, we move to third isomerism, that is called linkage isomerism. See the definition. Coordination complexes having same molecular formula, same set of ligands, but lone pair donor different. But the lone pair donor is different. Let's take, we are having two examples over here. If CN in cyno, if carbon is donating its lone pair, it will be called cyno. And if nitrogen donates its lone pair in NC, it is called isocyano. Similarly, SCN is called thiocyanato when sulfur is donating its lone pair, and when in NCS, when nitrogen is donating its lone pair, it is called isothiocyanate. Class, the fourth one is coordination isomerism. Let's have the definition first. Coordination complexes having same molecular formula, same set of ligands, but differ in arrangement of ligands and CMA in coordination entities. Class, there are two examples over here. Class, there are special type of coordination complexes where we find one is your cationic species, another one is your anionic one. Till now you have been doing either cationic or anionic species. Either cations was enclosed under coordination sphere or anions was enclosed under coordination sphere. But here what we find that both cationic and anionic parts are present always along with them. So here it is a bond between them is ionic bond. Here inside coordinate bond, but here the bond is ionic bond. Now class, most of the time platinum shows valency 2. So let's find out that how they are balancing each other. Class, if I put valency 2 here, ammonia has no charge, so it has valence oxidation number +2. So this coordination, cationic coordination species, yeah, sphere is getting positive 2 charge. Now see here, palladium +2, +2 -4 gives you -2. So now both are balancing each other. That's why the formula is right. Similarly here, palladium +2, and if I put palladium +2 -4 again gives you -2. So both the formulas are right. And let us find out first both whether having the same molecular formula. Okay, 1PT, 1PT, 1PD, 1PD, 4 ammonia, 4 ammonia, 4 Cl, 4 Cl. So they have the same molecular formula. But what we find? We find that in cationic part platinum is present, and here in cationic part palladium is present. In this case, in anionic part palladium is present, but in this case anionic part platinum is present. So that's why they differ in arrangement of ligands and CMA in coordination entities. Class, here we are going to have their nomenclature also, because that nomenclature I have not taken, because at that time you have not taught coordination isomerism. Now since that has been taught to you, so you see I am going to write out their name. First we are going to talk about always cation followed by anion, and if I am going to talk about cation, I will name ligand first followed by CMA, ligand first followed by CMA, but it's anionic, so the name of the metal will end with word 8. So class, see the name: tetramine, platinum 2, no gapping, tetrachlorido, palladiate 2. Since palladium is anionic, so palladiate. Similarly, class, here name tetramine, palladium 2, tetrachlorido, platinate 2, platinate 2. So class, in this way the nomenclature can also be done. So class, we have taken all the 4 structure isomerism. First one was ionic isomerism, ionization isomerism, second hydrate isomerism, third linkage isomerism, and this was your 4th coordination isomerism. Now we'll move to the second part of isomerism as a whole, that was your stereochemistry. Class, stereoisomerism in coordination complexes. Let's have the definition first. Coordination complexes with same molecular formula but differ in arrangement of ligands around CMA. Differ in arrangement of ligands, this is the metal, and arrangement of ligands in space. If it differs, it gives rise to stereoisomerism. So I repeat again, differ in arrangement of ligands around CMA in space give rise to stereoisomers, and we are moving to types of stereoisomers. The first type is your geometrical isomers. Class, we have been studying only three geometry: tetrahedral geometry, square planar geometry, and octahedral geometry. Let us discuss one by one. Now, let us take the first case in the tetrahedral. Class, this is the position of central metal atom. I can show you with one example. See my hand. Imagine this is the metal, and we are having four legends surrounding it. This is called tetrahedral arrangement. First legend, second legend, third legend, and fourth legend. Class, what do you find? We find that all have equivalent adjacent position. See, adjacent position, similarly adjacent position, similarly adjacent position. So all are having similarly adjacent position. Therefore, geometrical isomerism is not observed. No geometrical isomerism is observed. So class, in the tetrahedral isomerism, in tetrahedral geometry of geometrical isomerism of coordination complexes, we find that all ligands are having similar position adjacent to the central metal atom. Therefore, no geometrical isomerism is observed. Now let us move to square planar. In square planar geometry, you see it's having square shape, surrounded by four ligands 1, 2, 3, and 4. Very simple to understand. See, L1, L2, L2, L3, L3, L4, L4, L1. These are adjacent position, and if similar groups are present on these adjacent positions, they are called cis. But if similar groups are present on L1, L3, L2, L4, they are called trans. See, if similar groups are present on L1, L2, L2, L3, L3, L4, L4, L1, they are called cis. And if they are present at L1, L3, L1, L3 opposite, L2, L4 opposite, then they are called trans. Let us see example here. Metal, 2Br and 2Cl. Br occupying, Cl occupying adjacent position. That's why they are called cis isomers. But in this case, what do you find? 2Br occupying just different opposite positions, as well as Cl as well as Br, both are occupying opposite positions. That's why not adjacent positions, and hence this one is your trans. So if similar groups on the same side, they are giving rise to cis isomer. Similar groups on opposite sides, they give rise to trans isomer. Now class, the last one is your octahedral geometry, where we find that central metal atom is surrounded by 6 ligands: L1, L2, L3, L4, L5, and L6. Class, here you have to remember two things. What? L1, L6, one is up, another one is down. L2, L4, opposite. L3, L5, these three are called transpositions. If similar groups are present on N1, L6, L2, L4, L3, L5, they will be called trans, whereas other positions, they will be called cis. And one thing more, the ligands which are lower in number will decide. Let us take example here. A central atom is surrounded by 6 ligands: A, similar types, 4 types, and B, similar types, 2 types. So 4A and 2B are present. So B is going to decide whether the molecule is going to be cis or trans. So in this case, we will never see position of A, we will simply see position of B, because B is smaller as compared to A, having only 2 atoms here, lone protons. So class, let us see here. We find that 2Cl and 4Br are surrounding 1CMA, and since 2Cl positions are just opposite to each other, one is up, other one is down, So Cl is going to decide here because Cl is lower in number and hence it will be called trans. Whereas in that case we find that two Cls are occupying adjacent positions, that is your cis positions, that's why we will call it cis. If Cl would have been here or Cl here or Cl here, it would have been called trans. But we find that these three positions are not there, L1, L6, L2, L4, L3, L5, so it will be simply called cis. So this is one is called trans and this one is called cis. So class, geometrical isomerism is found in three complexes: tetrahedral, square planar and octahedral. In tetrahedral, no geometrical isomerism is observed because they are occupying adjacent positions, similar positions. In square planar, same side, cis, different side, trans. And in this case, lower one is going to decide. L1, L6, L2, L4 and L3, 5 are trans positions, rest are cis positions. So this one we find that Cl occupying opposite side, so trans, Cl occupying same side, so it is your cis. So class, that was all regarding your geometrical isomerism in coordination complexes. Class, next topic in geometrical isomerism, that is the second topic, second topic in stereoisomerism, not geometrical, is your FAC and MER isomerism. I have already shown you in a glance. FAC, FAC and MER, MER, FAC and MER isomerism in octahedral complexes, and class, it arises in MA3B3 types. What does it mean? It means there are only two types of legend and both the legends are coming three times. A3, B3. So total 6, coordination number is 6. So such a octahedral complex where we find two legends coming three times, that is called MA3, B3 type. Now class, this one is your FAC, facial isomerism, or this one is your MER, meridional isomerism. Understand it very, very properly. See the definition. If three similar legends are present on triangular faces of octahedron, it is called FAC or facial isomerism. Class, see the diagram here. I have drawn an octahedral complex over here. There are 3 Br, 1, 2, 3. There are 3 Cl, 1, 2, 3. Now these 3 Br and 3 Cl, they are present at the triangular faces. You see, this is the triangular face. First face, second, and this one. So this is a triangle. So these three are present on triangular faces of octahedron. Similarly here also, see. Again it is forming a triangle. So three similar legends when present on the triangular faces of octahedron, it is called FAC or facial isomerism. The second one is your MER isomerism. This was your FAC, and the second one is your MER isomerism, MER. Class, what is the definition? The definition says, if three similar legends are present on meridian of an octahedron, meridian, this one is a meridian, right? So if three similar legends are present on meridian of an octahedron, it is called MER or meridional isomer. So class, you see here, 3 BRs are occupying the meridian, see, 1 BR, 2 BR, 3 BR, and they are just enjoying the meridian position, therefore they are called meridional isomers. On triangular faces, facial isomers. On meridian, they are called meridional isomers. So class, that was your second topic of stereoisomerism, that was FAC and MER. Now class, we are going to move to the last topic of stereochemistry, that is called optical isomerism. Now class, coming to optical isomerism, that you have been already studied in class 11, that texto and LEVO isomer. If people is rotated towards right, they will use to call texto, and when it is rotated towards left, they will call LEVO. That texto and LEVO is not here in your coordination complexes. Here you are only to find out whether the molecule will be optically active or not. Very simple. So class, there are two conditions. First, molecule should be asymmetric in nature. You know very well that if the molecule develops any element of symmetry, optical isomerism is lost. So first condition, same, that the molecule should be asymmetric in nature. And very, very important condition, if it should not be superimposable on its mirror images. You draw its mirror images and try to superimpose. If it is superimposable, then it will be optically inactive. But if it is non-superimposable, it will be definitely optically active. So class, I have already made a 2 example over here, and I am going to show you how to superimpose. So class, what I'll do, I will take this figure out. Just imagine in your mind that I am taking CL, PT, CL in a straight line and I am taking it out. So if I take it out along with BR, 4 BRs and try to put it here. So what I find that CL, PT, CL, CL, PT, CL is there, and in these 2 BR, this BR is there, and above these 2 BR, these 2 BR are there. So we get superimposable mirror images. Superimposable mirror images, therefore optically inactive because it should not be superimposed. Now class, let us take the second one. If I again take CLPTBR out, CLPTBR out, put it on CLPTB. Okay, these are the mirror images. So CLPTBR out, putting on the mirror image of CLPTBR, we find that CLPTBR and CLPTBR are on the same line, but on this BR we are finding this CL. BR matches, but on this CL we are finding BR. So ultimately, what I am getting non-superimposable mirror images. And if it is non-superimposable, the molecule will be optically active. Superimposable, optically inactive. Non-superimposable, always optically active. So class, whenever it has been asked to you that whether the molecule will be optically active or not, you simply draw a mirror plane, draw a mirror images and try to superimpose. If superimposed, optically inactive. If not able to superimpose, it is all optically active. Now class, coming to the last topic of coordination complexes, the topic is extra stability in metal carbonyls. Students, you all know that coordination compounds are highly stable, but coordination complexes having carbonyl as a ligand, they are found to be extra stable. Why they are found to be extra stable? The reason is that it is due to formation of synergic bond. What is happening? CO as a ligand donates its lone pair to CMA. See, CO donating its lone pair to metal. In all the cases, the same thing happens. Donates its lone pair to CMA, and in turn, filled D subshells of metals overlap with vacant anti-bonding MO, that is molecular orbital, overlap with vacant anti-bonding MO of CO, giving synergic bond, making it highly stable. In other complexes class, ligands only donate the lone pair, but synergic bond formation does not take place, so that's why they are not extra stable. But in metal carbonyls, we find that CO donates the lone pair to M, and in turn, filled D subshells of metal overlaps with vacant anti-bonding MO of CO, giving rise to formation of synergic bond, and hence it becomes extra stable. That is the reason that metal carbonyls are found to be extra stable. And class, that completes my entire coordination chemistry.